lecture 11 in the series on noise control in mechanical systems with Professor Sneha Singh, myself, and this lecture is the continuation of the previous lecture, that is the radiation from the common acoustical sources. So, previously we studied about what do you mean by wave structure interaction, and a wave structure interaction is essentially when it is from structure to fluid, we study radiation, and when it is from fluid to structure, we study the reception. And then we studied about some simplified acoustical sources, monopole, dipole, quadrupole, and their common and these sources as found in the various mechanical systems, what kind of machineries or mechanical systems generate these kind of, behave as if these are these kind of sources and generate an appropriate sound field based on the type of source it is behaving like. Then we studied about the radiation efficiency. So, these concepts were introduced, which is denoted by the symbol eta, because eta for efficiency, and then source strength, directionality or directivity of the different sources, and then sound field, and how directivity or directionality is important, because suppose you have a particular source, then you know that what is the directivity pattern like. So, you know that at what zones the pressure would suddenly be low. So, one simple exercise, suppose you have got two unboxed speakers and you place them one behind the other. Okay. So, suppose you have got one unboxed speaker like this and the other unboxed speaker like this placed opposite to each other, they behave like an acoustic dipole, because these are like two monopoles. Okay. So, suppose these box speakers, these are boxed speakers, each of them, because in the market usually you find the boxed speakers. So, they behave like a monopole and they radiate. So, when you stand here, you hear a lot of noise, but when you stand here, you hear no noise at all. So, you can do these experiments in home and see for yourself that how it behaves, and how in certain regions the sound pressure could be quite high, whereas in certain regions they could be nullified and you hear very low sound pressure or very low noise. And another kind of inference we can draw is that if you see that in the market you get such boxed speakers, why do you get the speakers boxed inside the cabinets? Why are they popular? Because we studied in the previous lecture that the radiation efficiency of a monopole is much greater than the radiation efficiency of the dipole under reasonable frequency ranges, low to mid frequency ranges, where most of the sound sources are, common sound sources are. So, therefore, suppose we had a speaker and we want, the speaker usually is used for playing the sounds, music, various kind of music, etc., and we want to amplify it. Then how to do it? Very efficient, especially in the concerts, etc. We can have multiple such speakers and we want to amplify the sound. We can do it through the electronic amplifiers, but at the same time, if the same speaker you place it against a rigid backing, you either place it against a rigid wall or you place it or box it in this rigid wall, or you sort of enclose it in a rigid box, suddenly it becomes a monopole and the sound pressure or the sound emitting from the speaker, it amplifies in magnitude. So, that is why we have box speakers becoming very popular, because they are able to amplify the sounds, and also not just that, because they are able to amplify the sounds, but at the same time, because now they behave like a monopole, they have a uniform radiated pattern. So, That is why box speakers are more popular than the unboxed speakers, because they behave like monopoles. So, radiation efficiency is much higher, and at the same time they have uniform directivity, because that is what you want. You do not want that you place a speaker in a room and some people can hear the sound, some people hear it low, some people hear it high. We want a uniform directivity and a uniform distribution of the sound pressure. So, we sort of facilitate that it behaves like a monopole instead of a dipole. Okay, so in this one we will again see and continue our radiation from common acoustical sources, and then we will find out the radiation from the panels. It is an extended real life source, and then the various types of radiation fields. So, continuing from the previous lecture where we were finding the efficiency of a dipole with respect to monopole, let us now do that exercise for the quadrupole. So, the sound power of the quadrupole is given by this equation. So, let us find what is the radiation efficiency of this lateral quadrupole with respect to a monopole. So, this should be rho naught C k to the power 6 and the Wm is, as found in the last class, is rho naught C k square q square by 8 pi. Then this becomes pi. If you solve it, let us see what we result with. So, ultimately you would end up with k to the power 4 L1 square L2 square divided by 60. Okay. So, as you see here, for small low to mid frequency ranges, this term is even smaller than this term here that we had found for the previous case. So, which means that the radiation efficiency of a lateral quadrupole is much lower than the radiation efficiency of the dipole, which again is much lower than a monopole. So, from the noise control point of view, if suppose by some means we are able to convert a monopole source into a dipole, and even better if a monopole source can be converted into a lateral sort of quadrupole, then the radiation efficiency is going to go down heavily, and we are able to attenuate the sound waves that that particular source is generating. So, suppose we have a monopole source, by some way we can have another source coming up which becomes antiphase with it, then suddenly we can bring down the noise source. So, that is one of the inference we draw, and something which is a takeaway for the noise control engineers. Now, let us see the radiation from a real life source, which are these panels. So, large vibrating panels, you can find them in a lot of mechanical structures such as the cover plates, various kind of machinery panels, walls, enclosures, windows. You have so many panels, you just look around and you find so many sources or so many objects that are in the form of flat panels, large panels. Okay. So, it is one of the very common source of sound radiation, and the reason we are studying it is that it has a peculiar phenomenon. Till now, most of the sources that we studied, or the simplified source models, they were vibrating and they were creating the sound waves. And in the sound wave, what is the case? For a sound wave, whenever it is created and propagating in the medium, the speed is independent of the frequency of that wave. Okay. So, if the frequency is changing from F1 to F2 to F3, but if the medium is continuous and homogeneous, it will be a fixed C. Okay. The speed is independent of what frequency of wave you are creating. But when the panels, they vibrate and the waves pass through them, usually they are predominantly flexural in nature. Now, what do you mean by a flexural wave? It is different from a sound wave, because sound wave, they are longitudinal in nature. These flexural waves are transverse propagating mechanical waves. The definition of longitudinal and transverse waves has been given in the very first lecture. So, if you see what happens here, here the plate vibrates, or the particles of the plate or the mass that is vibrating in the vertical to the plane of the plate. So, although the wave is propagating forwards or downwards along the plane, the particles, they are vibrating perpendicular to the plate. So, you can, in the 1D, you can think that if you have a tight string or a tight rope and you struck it or pluck it, you will see these transverse waves where the disturbance propagates along the length, but the vibration is perpendicular to the length. So, same thing, if you now expand it to 2D, you understand the concept of this flexural waves. We also call these flexural waves as bending waves. So, what is the bending wave speed? We represent it as CB here in this lecture. So, here this is the overall equation for a bending wave speed. As you can see here, this omega is 2 pi f. So, the bending wave speed is directly proportional to the square root of the frequency. So, here in the bending wave, the CB depends on the frequency, unlike in a sound wave. Okay, whereas in the sound wave, it was independent of the frequency. So, and here we have this term B. B is the bending stiffness. For a flat plate, this is the equation of the bending stiffness. Okay. So, just a small correction here. Suppose mu is very small, then this B would be approximately E h cube by 12 when the mu is very small. Otherwise, this is the full equation for the bending stiffness of the plate, and rho s is what? It is the mass per unit area of that plate. Okay. Now, let us see here. This is a typical graph. You know that CB is proportional to the square root of the frequency. This is one of the graphs where we are plotting CB with respect to frequency f, and this is the square root dependence. As you know, the f is increasing, CB is also increasing, but not directly proportional, but in a it is not increasing as much as the increase in the f. So, just imagine, so this is imagine that we are increasing the frequency and you are observing that the CB as well increases, okay, following this relationship. So, there would be a point in time when at a certain frequency the CB, which is the bending wave speed in a flat plate, should become equal to the speed of sound in the surrounding medium, which in most of the cases is air. So, when CB becomes equal to the speed of sound in the surrounding medium, then that particular frequency, we call it as the critical frequency. Now, there are three different types of zones of consideration. One is below the critical frequency. So, till the time the bending wave speed is smaller than the speed of the sound in the surrounding medium. Okay. So, most of the cases it is the air, but it could be water also. So, if you have a kind of plate in a water or any other medium, the same will hold true. So, this is what? This is the speed of sound in the surrounding medium. Okay. So, till the bending wave speed is below the critical frequency, there is no sound radiation that happens from these plates or panels. Okay. Then comes the region where you have a critical frequency when CB becomes equals to C, and when you equate it in this equation over here, so you put this CB as C and you find out the corresponding Fc that is creating this C. So, from this equation if you solve, you will ultimately get that this critical frequency is C square by 2 pi under root of rho s by B. So, at that moment when these are becoming equal, you will have maximum sound radiation. Okay. There is a perfect matching that is happening and the radiation efficiency is actually the highest. Then above that, above the critical frequency, okay, the sound radiation happens, but at a lower rate. So, what we see here is that below the critical frequency, the same plate is not able to generate sound waves, even though it is vibrating, it is having a bending wave, but it does not act as an acoustical source and it does not radiate away sound waves. At the critical frequency, suddenly there is a fixed high radiation and then below that radiation goes down, but it is there. Okay. So, this radiation, so here let us say this was the plane of the plate which is along xz plane, and then the sort of plate there is some flexural wave that is set in the plate in the xz direction. So, we are showing a 2D view here. So, this is a transverse wave. So, the direction of the propagating wave is along this xz plane along the x axis here. The wave is propagating like this. How do you find out the relevant direction of the sound waves it is creating above the critical frequency? So, if you draw the lines parallel to this waveform at the trough. So, from the trough you draw these tangential lines, okay, from the two successive troughs, and then a perpendicular line from this. So, that gives you the direction of this particular thing is the direction of the sound waves it is creating. Here the distance between these two troughs becomes the lambda of P, rather I should call this lambda of B because it is a bending wave. Okay. And this is what? This is the lambda of the sound wave it is generating. You can see that the lambda of the sound wave is smaller. So, what you see here is that the lambda of the sound wave is smaller, but the frequency obviously is the same. Let us see an interpretation of this. Lambda is what? It is given by C by frequency. For the bending wave, lambda B is CB by F, and for the sound wave it is creating, this lambda is C by F. The F is the same, but CB is greater than C. So, lambda B is greater than lambda, as you can see here graphically. Okay. That happens above the critical frequency. Now, some of the sources of flexural waves in mechanical systems. Now, let us get and see what happens in the mechanical systems. You have large roof panels, and then various machineries have large panels, large roof panels, and any kind of panel or flat plate surface would be acting as a source of flexural waves and would be able to radiate the sounds above the critical frequency, not below it. So, what could be a design consideration with respect to if suppose a noise control engineer looks at this particular phenomenon? So, what is the inference or a takeaway for a noise control engineer? So, the design consideration for a noise control engineer is that you have to design the panels in such a way that they have a high critical frequency. Okay. So, this value here has to be high. How it can be high? When you increase the bending stiffness or you reduce the mass per unit area. So, basically you can make it to have a high critical frequency when you either increase the bending stiffness or you reduce the mass per unit area. In that case, their critical speed is very high, and hence at a higher frequency there is a matching. So, because below the critical frequency we do not have radiation. So, the higher the critical frequency, then the operational frequencies of these machineries. So, if the critical frequency is higher than the operational frequency, then it will not be able to radiate. So, that is the aim. And from the finite panels, there is a resonant response, which means that they are able to have large amplitude of vibrations when the natural frequency matches with the vibrational source frequency. Now, types of radiation fields. So far we saw that different sources, they are having different fields. A monopole is having a spherical wavefront and a spherical wavefront distribution, a dipole is having a dumbbell shaped distribution, and so on. But all of that distributions that we obtained was under a condition that the radiation is obtained in a far field with a free field propagation. It was not representing the near field effect. So, how the source behaves and how the sound waves propagate, all of that is only valid within a certain extent in the spatial dimensions. So, there are different fields associated with it, and so far all the fields that we studied in the previous lecture and so far, in all the equations we dealt with in the previous lecture, they were free field propagations. So, what do you mean by a near field? Suppose you have a source, so very near to the source, the pressure and the velocity, they are not in phase. The wavefront has very complicated shapes. Okay? They are non-propagating waves, also called as evanescent waves. Okay? And then as you move a bit away, you finally reach the far field region where acoustic pressure and particle velocity, they come in phase and the wave becomes propagating in nature and you get the far field. So, whatever radiation field we studied or the equations we derived, it was for this region, not for the near field. In fact, near field is where you should not be making any measurements or doing any kind of acoustic manipulation, because they do not truly represent a sound source. Suppose you have a machinery source, the near field, the sound source could have a very complicated kind of shape. So, if you made the measurement of the machinery in some places here, okay, in some places here, it would not truly represent how the source behaves at a large scale. Okay. So, you cannot extrapolate whatever you find to the regions beyond a certain level, beyond a certain extent. So, in general, the practice is that whenever we try to measure the noise of any machinery, we keep a certain distance. It is not like we have a machinery and we directly place a microphone just next to it. It is not going to give us the true representation of the field from that machinery source. Okay? So, we have to move to the far field where finally they become in phase and propagating in nature. So, what happens, so how do you determine what is the extent and what is the extent beyond which we have to make the measurements to get a true representation of the source? So, the near field, it depends on the source frequency, the size of the source, the phasing, and in general the near field region for a source is somewhere between the surface of the source to up to 1 to 2 lambda from the source. So, 1 lambda to 2 lambda from the source. So, let us say if this is some source, okay, which is sort of creating these sound waves, then the near field region is, and this is the distance r from the surface of the source, then the near field region starts from r is equal to 0 till around 2 lambda to be on the safer side, beyond which we have the far field region. 2 lambda till almost infinity in case of open case, we have the far field region. Okay. So, we do not make measurements in the near field. Okay. Measurement is not recommended in the near field. As already stated, it is not a true representation of the source. There are a lot of near field cancellation that happens, and it is only after that that it starts behaving like what we have studied. Okay. So, that is the thing. Now, let us see some of the types of radiation fields. We have seen the near field and the far field so far. We also have another radiation field called as the free field. Free field is what? It is a region where the particles, they are aligned with the direction of the wave propagation, the pressure and the velocity are in phase, and in addition to that, there are no reflections, all the sound that is reaching a point is directly coming from the source. So, if you see here, this is what happens in the far field, all of the above conditions, and this is what happens, these conditions is what happens when there are no obstructions or change in media. So, the media remains infinite and homogeneous without any change in media occurring. So, free field can essentially be a far field plus no reflection condition. This particular photograph, so obviously in the real life a perfect free field is almost impossible to achieve. Okay, we cannot achieve a perfect free field, but we can try and come to a near free field. So, this again is a photograph from one of the research we did for sound source localization. It has been published in various journals which you can Google and have a read for yourself. So, what happened here is that we have an open football stadium where the nearest obstructing surface is far away, many lambdas away from the source, and we have a box speaker, it is acting like a monopole, okay, and it is almost 1.5 meters above the ground to avoid the reflections from the ground, and all the reflectors or any kind of change in the media or any kind of new medium or surface or structure is quite far away from the source. So, here it is acting like a near free field where you are getting a propagating wave. So, what is happening in the free field? All the equations we derived, the equations for sound wave propagation, the equations for sound wave propagation in the medium boundaries, all of that, they are true in the free field. So, in the free field spherical waves, they follow this kind of attenuation rate. The P RMS is inversely proportional to R, okay, and in the cylindrical waves, the P RMS is inversely proportional to root of R. Now, I would like to here state that in the previous lecture, I think somewhere I mentioned P is inversely proportional to R square. So, just rectify that, it is inversely proportional to R, it is the intensity which is inversely proportional to R square. The pressure is always inversely proportional to R. So, just rectify that in the previous lecture. Then this is what happens in the cylindrical waves, whereas for the plane waves it remains constant. Then this equation that we had derived for the intensity, which is P square by rho c, then P by U is rho c. All of these equations, they are valid for free field propagation. What is the location of the free field? So, here obviously you have to be in the far field and away from the reflector. So, both the conditions have to be satisfied. So, for both for compact sources as well as for the extended sources, we have the same condition or location for a free field. The distance from the source should be much greater than the lambda under consideration, and the distance from the reflector also has to be much greater than the lambda. So, any nearest reflector, you can say the distance from the nearest reflector. Okay. So, then the last type of radiation field that we will deal with is the reverberant field. This is a snapshot of one of the boxed cabinets in our department that I took today, and I wanted to paste it and show you a reverberant field. So, what is happening here? This is a large cabinet that is surrounded from all the sides with hard reflecting walls, and then it is covered by glass on the other end. So, here you have a glass covering, so, and all the back walls, they are hard walls, and here what you have, small enclosed space with a lot of hard walls that are able to reflect the sound source. So, what happens here is that what is the reverberant field? It is a region where acoustic particles are aligned with the direction of wave propagation. The pressure and velocity are in phase, but there are significant reflections as well. Okay. So, here at any point P, suppose we had a source in this field and we measured it at any point P1 or P2, what would we get is that here the sound would be both P from the direct field plus P due to reflected field in both these cases, which means that the sound is arriving directly from the source, but also that same sound is reaching these reflecting walls, and it is getting reflected and reaching the listener from multiple pathways. So, essentially what does a reverberant field do is it amplifies the pressure compared to what you would observe in a free field, okay? And the attenuation rate that is expected in the free field does not hold true for a reverberant field. In fact, if you have a perfect reverberant field, typically you experience a uniform distribution in the acoustic pressure, irrespective of the fact that if it is a spherical wave, it should attenuate at the rate of inversely proportional to r, or cylindrical then inversely proportional to root r. That is for free field. In the reverberant field, almost uniform distribution happens if it is a perfect reverberant field, and the pressure amplifies because it is both the direct pressure. So, all of this was what? The direct pressure coming from the source. So, the direct pressure plus the indirect pressure coming from the deflected pathway. So, overall the acoustic pressure amplifies, and that is why you observe that suppose you are moving around in, let us say, I will again come back to that football stadium, very large football stadium or very large open field, and when the players they are playing and they are shouting at each other and still the noise level is down. When they have to communicate with each other, they shout at each other because they are in a free field environment. But when the same players they come in a closed room environment, so the same person who was talking in an open field, now suddenly they start talking in a closed room environment, the pressure level actually feels very high because it is a reverberant environment. And that is why even in parties you experience that suppose you have got some DJ or some speakers that are in an open environment in the parties, then it does not bother you much. But when you put the same DJ and the same speaker system within a closed reflective room in a party, and you will not be able to hear a thing, you will not be able to communicate properly because the sound level will amplify, because now we have reached a reverberant environment. Now, typically in practice, you do not, ideally you do not get a perfect of any of such field. Suppose this is a machinery source, this is where it is placed, the nearest reflector is here, this is the nearest reflector. Then it starts from the near field, then you have the far field. Within the far field, for a certain region you have the free field propagation, but then near these walls you will have the reverberant field. And it is always recommended to make the measurement in the free field, because there you expect and you can get a sense of the type of wavefront. Okay, so with this I would like to close this lecture. Thank you for listening.